In previous videos, we learned 4 basic proof methods: direct proof, proof by contraposition, proof by contradiction, and proof by cases. Next, we'll learn another powerful proof method called induction. More specifically, in this video, we'll talk about induction, and in the next video, we'll talk about another form of induction called strong induction. First, let's consider the following stair climbing scenario. Assume that you know the following 2 statements are true. First, you can reach the first step at the bottom of the stair. Second, once you get to a step, you can always climb to the next one up. So based on these 2 statements, what can you conclude? The conclusion is you can reach any step of the stair. Now let's formally formulate this stair climbing scenario. Assume that the steps are numbered by 1, 2, 3, etc. And we use Pn to denote that you can reach nth step. Then the first statement becomes just P1. It means you can reach the first step. The second step can be translated into, for any integer k, if pk is true, pk plus 1 is true. And you can see, if you can prove these 2 statements are true, then Pn must be true for any positive integer. This is exactly the key idea of induction. Here are the induction rules that we'll use to prove the property of objects that are in order or can be indexed. The rule says, let P be a predicate on positive integers. If 1, P1 is true. 2, for any k, pk implies pk plus 1 is true. Then Pn is true for all positive integers. Note that here 1 really means the first element that has this property P. Many of you may ask why induction works, or in other words, why, by knowing only these 2 are true, we can prove Pn is true for all positive integers. I'm going to explain by using an example. Let's say you want to prove P5 is true. How do you show P5 is true from these 2 steps? First of all, since this is true, using universal instantiation, we can conclude P1 implies P2 because k can be equal to 1. And then combining this one with P1, we can prove P2 is true. Then we use this UI rule again on the second statement. We can conclude P2 implies P3. Then combining these 2, we can imply P3 is true. So now you can see the pattern. You can repeatedly apply the UI rule on this one and to prove P5 is true. And by repeatedly using this UI rule, you can actually prove Pn is true for all positive integers. And based on those rules, we know that proof by induction has 2 steps. Step 1 is called basis step, where you need to prove P1 is true. And we call 1 the base case. Note that sometimes it may be necessary to prove this property for multiple base cases. We'll see some examples later on. The second step is called inductive step, where you need to prove for any k, pk implies pk plus 1 is true. How do we prove this one to be true? What you can do is you assume that pk is true for an arbitrary positive integer k, and then you show that pk plus 1 is true. That's how you prove this inner implication is true. And then you can use the UG rule to generate these two for any k. pk implies pk plus 1 is true. And in this step, we call the assumption that pk is true the inductive hypothesis. Next, I want to show you the template for proof by induction. First, if necessary, you should translate the statement to be proved in the form of for all n greater than or equal to b, Pn, where b is the first element that has property p. And then, since proof by induction has two steps, for the first step, you need to write the keywords basis step. And then just show that the base case or cases all have this property p. In other words, you show that PB is true. And second, you write the keywords inductive step. And in this step, we have three sub-steps. First, you state and clearly identify the inductive hypothesis. Basically, you say that assume that pk is true for an arbitrary integer k, which is greater than or equal to b. Of course, depending on the statement you want to prove, you should translate pk accordingly. Next, you state what needs to be proved under the assumption that the inductive hypothesis is true. In other words, write out what pk plus 1 says. Last, which is the most important substep here, is you want to prove pk plus 1 is true using the inductive hypothesis. And finally, you can signal the end of the proof by stating the conclusion. Next, let's see three examples on how we can use proof by induction. This is the property of the positive integers that we want to prove. Therefore, this is P, which is an equation. And at the very beginning of the proof, you can see we state the game plan that we're going to use induction to prove this statement. And then, in order to avoid writing this long summation in the proof, I'm going to introduce a notation. F of n equals 1 plus 2 plus 3 all the way to n. Oh, by the way, we use ellipses to represent the omitted part of the summation. So now we have f of n, which can make the writing of the proof easier. According to the template, next one will be the basis step, where you prove this property is true for the base case. And in this example, the base case is n equals 1, because 1 is the first positive integer. How do we prove 1 has this property? Basically, to prove the left side of this equation is equal to the right side of the equation, where you substitute n equals 1. And clearly, you can verify that on the left side just equal to 1, and right side is equal to 1 as well. This is how we prove P1 is true. Next, inductive step. Again, according to the template, you first state the inductive hypothesis, which is pk is true for any positive integer k. What is pk here? pk is f of k is equal to k times k plus 1 over 2 for any positive integer k. Then we state what we want to prove to be true, which is pk plus 1. What is pk plus 1? Pk plus 1 is fk plus 1 equals k plus 1, because n equals k plus 1 times k plus 1 plus 1 over 2. This is your inductive hypothesis. This is what you want to prove to be true, which is pk plus 1, using this inductive hypothesis. So now, how do we prove this to be true? Since this one is an equation, in order to prove an equation to be true, you can start from one side and prove that it's equal to the other side. So here, we're going to start from fk plus 1. What is fk plus 1? Based on the definition, it's equal to 1 plus 2 plus 3 plus k plus 1. Okay? Now what do we do? Here is where we are going to use the inductive hypothesis, because this part is just equal to f of k, correct? Then, by inductive hypothesis, fk equals this one, k times k plus 1 over 2 plus k plus 1. And what's this one? This one is equal to, if you look at the two ends of this equation chain, we have proved that pk plus 1 is true. Then you can say that you have proved the original statement is true for any positive integer n. Second example, we want to prove this property, which is an inequality, is true for any positive integer that is greater than or equal to 4. And again, at the beginning of the proof, we state a game plan by saying that we prove this statement by induction. According to the template, we first prove the base case has this property P in basis step. What is the base case here? Or in other words, what is the first element that we want to prove to have this property? It is n equals 4. Now, does 4 have this property? We can substitute n equal to 4 into this equality and check that. 4 squared, which is equal to 16, is greater than 3 times 4, which is equal to 12. So basis step is done. Next, inductive step, where we need to prove for any integer k that is greater than or equal to 4, pk implies pk plus 1. And according to the template, we first state pk is true. What is pk? Pk is k squared is greater than 3k for any positive integer k greater than or equal to 4. Next, we will state what pk plus 1 means. Pk plus 1 in this example means k plus 1 squared is greater than 3 times k plus 1, which is equal to 3k plus 3. And next, we're going to show how to prove k plus 1 squared is greater than 3k plus 3 using the inductive hypothesis. So in order to prove this inequality, we'll start from the left side. K plus 1 squared is equal to k squared plus 2k plus 1. Now, how do we proceed? Look at the inductive hypothesis. It says k squared is greater than 3k. And here we have k squared. So we're going to use the inductive hypothesis here. So now we have this one is greater than 3k plus 2k plus 1. Now you compare what we need to prove with what we currently have. We have 3k here, we have 3k here. So we're going to keep it untouched. Then how do we deal with this one? Comparing these two, you can see if you can prove 2k plus 1 is greater than or equal to 3, then we are done with the proof. How do we know that? Don't forget that we assumed k is greater than or equal to 4. Therefore, this is greater than 3k plus 8 plus 1, which is of course greater than 3k plus 3. Now, looking at these two sides, two ends, we can see we proved k plus 1 squared is greater than 3k plus 3, which is pk plus 1. And therefore, we prove that for any positive integer k that is greater than or equal to 4, pk implies pk plus 1. That is inductive step. Then combining this basis step and the inductive step, we proved the original statement is true by induction. Last example. We want to prove 7 to the nth power minus 2 to the nth power is divisible by 5 for any positive integer n. Here, Pn is this part. In the basis step, we'll prove this P is true for the base cases. What is the first element that has this property? Since it says any positive integer n, then the first one should be n equals 1. Now, does 1 have this property? You can substitute n equal to 1 into 7 to the nth power minus 2 to the nth power, which is equal to 5. Now, obviously, 5 is divisible by 5. Next, inductive step. In this step, we're going to first state the inductive hypothesis, which is 7 to the kth power minus 2 to the kth power is divisible by 5 for any positive integer k. And then we need to show 7 to the k plus 1th power minus 2 to the k plus 1th power is divisible by 5. How do we show that? Let's first see how we can represent 7 to the k plus 1th power minus 2 to the k plus 1th power. This is equal to 7 times 7 to the kth power minus 2 times 2 to the kth power. Some of you may ask, how do you know we should represent this way? The reason is we want to use the inductive hypothesis. And in the inductive hypothesis, both the exponents of 7 and 2 are k. That's why I just factored out 1, 7 from this and 1, 2 from this in order to make the exponents k on both of them. But now, how can we use the inductive hypothesis? And in order to use the inductive hypothesis, what we can do is let's subtract a 2 to the kth power here. But in order to make the equality still true, we need to add this back. And you can verify this is equivalent to this. Okay? Now, what can we do? According to the inductive hypothesis, we know this is divisible by 5. And when we multiply it by 7, this is also divisible by 5. So we do not need to do anything on this one. What about this two? Well, the good thing is for this two, you can factor out 2 to the kth power. So you have, now you can clearly see, since it's equal to 5 times 2 to the kth power, the second term is also divisible by 5. Of course, the summation of two terms which are divisible by 5 is also divisible by 5. So you can see we finished the inductive step, and then combining the basis step and the inductive step, we proved the original statement is true for any positive integers. And next, there are 2 exercises I would like to work on after you watch this video.